Good afternoon. Thanks everyone for joining our session today. We're going to be talking about big data, analytic, data-intensive applications, and how they work when using Ceph in an object storage capacity. So we'll start with the background that led us to kind of start doing this work. About a year and a half ago, we kind of met together with a number of our customers because they were actually doing a lot of working on bringing their big data workloads into their OpenStack environments. And one of the things that was important for them in order to make that possible was to consume object storage as the main persistence layer for data. So most organizations at some point brought a Hadoop environment into their business. And things were fine when it was kind of a singular environment. They maybe had one or two workloads or maybe a couple different teams that are working within the confines of this kind of singular Hadoop cluster. But as the years went on, this has kind of expanded to multiple teams and a lot of different demanding workloads. And the number of tools that are available for processing data in these environments has kind of, there's been this Cambrian explosion. So instead of just having kind of one common MapReduce style partition for interacting with the data, they're using Spark SQL, they're using Presto, they're using Impala, they're using all these different tools to analyze the data. And with these different teams and different workloads competing, they have a lot of problems with being able to isolate compute resources or managing different versions of different software. One team may have a kind of a robust pipeline and they don't want to disruptively upgrade to a newer version of the analytics software, but there might be another team that's working on, they want access to the latest machine learning libraries, and so they want the latest version of Spark and whatnot. So there's kind of this mismatch between their different priorities. So with all these different technologies, there's really kind of, they're overall built into these different pipelines. And so there's data generation. Data is coming in from streams or it's bulk ingested in. And then once it's in the persistence layer, they're transforming it into different formats. Maybe they're reserializing it into a columnar format. They're joining data sets together. And then they're doing things like data analytics for querying, business reporting, kind of data discovery, exploration, trying to figure out new insights from their data, or even using this corpus of data to train machine learning models so that they can make more intelligent applications. So kind of mapping some of the different tools to the different components of these pipelines on the data generation side, from clickstream data, from different web applications, sensors, call detail records maybe, and then probably commonly used for streaming. We have people using Kafka, and then ingest, we see people ingesting directly out of Kafka, NiFi, or some sort of traditional application. And then using tools like Hadoop and Spark to transform that data into a more consumable format for analysis and various other data science activities. So going back to the problem, going from kind of this singular environment with very few consumers to a very multi-tenant environment with all these kind of conflicting demands on the infrastructure. So, what is the evolution? What does the platform need to evolve to in order to better cater to all these different teams, all these different workloads, and all these different tools? So there's three kind of overall approaches that you can take. Now Hadoop was obviously made to scale out, and so kind of the natural least friction path is just build a bigger one, right? You can always build a bigger environment and hope that through brute force you're able to mask kind of the performance issues of of having a lot of different workloads and teams competing for resources, and hopefully you're able to do some smart things with maybe various queues and a yarn scheduler that will make things okay. Or more commonly, what we see with customers where they're at today is different teams and different workloads are trying to hit different SLAs, and so they ask for their own cluster and they get it. But the problem then arises when you have these multiple different teams with different data sets, and then you want to create some sort of composite data set or join data between these two different clusters. And so they end up copying and rehydrating data from one side to another. So now you have two copies of the same data set in two different siloed kind of data platform environments, which is expensive because you have that replication, but then each of the individual environments is doing their own replication inside that environment. So it's very, very expensive. Or the third solution, which is kind of use a centralized data set storage place, in this case object storage, and then spin up clusters as necessary, workload-specific clusters in an OpenStack environment. So what are some of the challenges of just building a larger cluster? Well, we find from our conversations is that a lot of customers have very difficult time achieving their SLAs when they take this approach. It's very difficult to isolate compute resources in a single large cluster, even with the scheduling logic that's available in kind of the traditional big data scheduling systems. And the biggest thing is it lacks elasticity. And elasticity is not just the ability to scale out, but it's also the ability to scale back in. So it's very difficult for one team to relinquish resources for another team to use, or for them to request more resources so that they can scale with the increased workload. It's, they got to procure additional hardware, have it deployed into the data center, bring those, that new hardware into the cluster. It's very, very time consuming, and they need something more rapid, more agile. So the multiple smaller clusters is nice because it kind of addresses the SLA concerns, and that the different teams that have different workloads can kind of isolate their compute resources, and that way they're able to hit the service levels that are required for their applications. But it comes at an expense. When they each have their own distinct storage silo for each of these environments, the overhead, like I was suggesting before, is very high, because you're copying between data sets, or copying these data sets between clusters. They're each doing their own replication, and it makes it very complicated if you need to track data lineage for some sort of to understand the relationships between parent and children of the data set. So if you have a data set A in one cluster, you have data set B in the other cluster, and you want to make a composite data set, that's data set C, that is joining those two data sets together, and you have copies of A and B in two different clusters, then keeping track of which one is the single source of the truth can be very, very complicated. And still, each of these individual environments lacks the elasticity. It doesn't have the ability to scale in, doesn't have the ability to scale out, because it's just a fixed environment. They need to procure additional hardware, and that doesn't work so well. The third, and the approach that we're recommending to folks, is to have on-demand analytic clusters with a shared data lake. And in this case, the shared data lake that we have done a bunch of joint testing with Intel is using Ceph in an object storage capacity. And so what you get from this is different workloads and different teams are able to provision their own analytics environments inside of OpenStack just by making API calls and provisioning additional Nova instances in order to scale out their workload. And because the storage is not part of the ephemeral storage of the compute nodes, or as Cinder RBD devices, they can elastically scale up and scale and contract that back in without having to worry about storage shuffling around because it's persisted outside of the analytics cluster. It's not in the virtual machines. By eliminating the duplication across the multiple storage silos, it also saves a lot in terms of the amount of capacity that's required for these sorts of the data lake, right? So instead of having multiple copies, you maybe are using one erasure-coded store. So instead of even having the overhead of 3x replication, but then in addition copying that to multiple data centers, you just have one copy and all the clusters kind of face into that one copy, and it's maybe erasure-coded, so it has 1.5x overhead instead of 3 or 9 times maybe if you have copies in multiple environments. Because they're elastic, because you can expand these analytic clusters and you can contract them and relinquish the resources back into the OpenStack cloud, it makes it so that you eliminate kind of the idle resources. There's a lot of folks that I've talked to that when they bring their big data environments or workloads into an OpenStack cluster, the data platform team that provisions those environments never relinquishes the data or the resources back to the organization because they're running HDFS inside of their compute resources, and if they terminate their VMs, they lose their storage and it's gone. But by pushing storage down to be an infrastructure level service, you have the ability to scale out, but back in more importantly. And it increases the agility, right? So when you're dealing with APIs, you're just provisioning new instances through Nova. You can very quickly spin up a new workload cluster to test some sort of new idea, test some new versions of software, or to just provide an ad hoc data lab for a developer or data analyst that needs to work through a data set. The other great benefit of this sort of architecture is that you have this public-private architectural fidelity. So if you look at the kind of the best practices and what the Amazon or Amazon, but also the Netflix, the Airbnbs of the world, the architecture that they've adopted for their big data applications is to persist all their data into their case, because they're in the public cloud, AWS S3, and then manage different workload clusters in EC2. We want to extend those same modalities into the private cloud. So where you're provisioning instances through Nova APIs and you're persisting data into either through the S3 API or through the Swift API with Ceph. So kind of the original, the generation 1, you had this monolithic Hadoop stack. They provided very single purpose infrastructure, scheduling and storage that was tailored to specifically for analytics needs, and they provided the analytics software on top of that. And I think, and what I would say is that the new generation is decoupling the stack, and analytics vendors focusing more on providing analytics software, and then the storage and the provisioning aspect gets pushed down to the infrastructure layer because that's a more general thing that's needed more broadly across the entire organization, and it's kind of generic infrastructure that can be used for things outside of the analytics space. So if you have a lot of media content that you need to store, that can go into the object store. If you have all these other sorts of applications, you're going to be provisioning them in OpenStack. So it's more general purpose, and so it spans a wider set of use cases than just the analytics-specific infrastructure. So now, we'll talk a little bit about some of the testing we've done.
Okay. So good afternoon, everyone. I'm Yuan from Intel. I'm going to introduce some findings we've got during our tests in Intel Labs. So here's a simple introduction for the workloads. We have 4 types here. Actually, the first 2 are micro benchmarks like DFS-IO, TerraSort, and also ETL workloads. Last one is we picked like 54 queries from TBCDS, and then we do those batch analytics workloads for this big data solution. So this is a performance overview for our testing cluster. Basically, we got two takeaways from the testing. The first one is by upgrading to Hadoop 2.8, the performance improved a lot, nearly triple X times. And the second one is with all-flash Ceph, the performance is much better than HDD-based Ceph. 10-node AFA cluster is almost on par with 16-node HDD cluster. Okay, I'm going to introduce the details here. So this is the first generation of our testing cluster. You can see there are actually 3 tiers. The first one is on the upper side is computing tier. We have 5 compute nodes, each with 2699. That's the top bin for Broadwell CPU. And each compute is installed with 2 SSDs for shuffle device. And for the software, we actually use Hadoop 2.7 and Spark 2.1 at first, and then we upgrade to the newer version. For the accessing tier in the middle, initially we are using 2 Redis gateway and also a load balancer. Network configuration is like for 40 giga on the front, and for Redis gateway, each has 20 giga for the in the front and in the back. And also in the storage tier, we have 5 Ceph nodes, each with 1 P3700 as the general device, and 4 S3510 SATA SSD as the data device. So with this architecture, we did lots of testings. The first one is we found with the default configuration, those queries we picked from TBCDS is not 100% success. We have to tune a lot. For example, with maximum timeout value for the Spark tasks, and also the memory compute ratio for the Spark tasks. Then with our tunings, we can get those queries successfully running. Then we checked those logs from Spark and also from Redis Gateway. We found that there are lots of new connections on each segment. From the right picture, you can see in each 2 seconds, there's about 20 new connections for Redis Gateway, which means we also found there's lots of 500 errors in Redis Gateway log. So we then did more analysis on Spark side, and we found there's a S3A parameter for this. In Hadoop 2.8, there's a tuning called S3A read ahead. Basically, it tries to tell the S3A clients that is a random read or sequential read. If you enable this, S3A will try to treat those data as a random read and reuse the last connection. So by enabling this feature, we found the performance improved a lot. From the up picture here, you can see the performance is almost triple X improved. The picture, last picture here is trying to show the HDD-based cluster versus SSD-based cluster. If you look at the deep blue pillow, the performance is almost the same. But we have only 10 nodes for SSD cluster, but 64 nodes 60 nodes for HDD cluster. So from a TCO perspective, SSD cluster is actually better. Okay, so we've done the first round tests, and we are trying to figure out which is the bottleneck. Obviously, in the previous architecture, load balancer is going to be the bottleneck. We then checked the network traffic, and we found the best maximum network bandwidth is like 2.5 giga. We then changed our configuration with more advanced connection tier. So the compute tier and the storage tier isn't changed. But in the accessing tier, we switched to more Redis gateway servers and also a round-robin DNS-based access. So with this, we saw the bottleneck on load balance side is fixed, and also we saw about 18% performance improvement with round-robin-based DNS access. And for some of the queries, like Core 42 here, it has about 1.64x faster than in the new architecture. Okay, so this is the resource utilization here. We can see from the right picture, network bandwidth is going to improve a lot. Then we're trying to do more improvements for this architecture. With more Redis gateways, obviously you can improve the performance, but the TCO is also going to increase. So we're trying to co-locate Redis gateway with OSD. You can see from this picture, the accessing tier is gone, and we are now using co-located Redis gateway with OSD servers. Each OSD server is deployed with a Redis gateway, and the network configuration is specially configured with multipath configured, actually. So we can separate Ceph public cluster network and also the Redis gateway network. So by using this architecture, we can see the performance actually doesn't change much. But obviously, we saved 5 accessing nodes and also the network NICs. So the TCO is much less. We then did more tests with Redis gateway scaling. In the previous configuration, we only set up one Redis gateway for each OSD server, and then we tried to use more Redis gateways for each server. For example, for each OSD, we use 2 Redis gateway instances to see if the performance improves. And we got some findings here. So as the instance of Redis gateway increasing, the DFSO workload and also ET workload can improve. But if you have like 4 to 5 Redis gateway instances, the performance doesn't got much change. So that's the finding here. Basically, you should do a test based on your configuration to see which is the best configuration. Okay, we then went to further tests with another configuration. So initially, we have 2 SATA SSDs on each compute to do the shuffle work. We then asked, could we remove that device? So we did this experiment. We actually mount 2 Ceph RBDs to each compute, and then use that Ceph RBD to play as a shuffle device. So during our tests, we found that the performance is not impacted a lot. So if you look at the yellow and the blue pillow here, some of the core arrays has even improved. This is because we have actually we have an all-flash array Ceph cluster. The maximum bandwidth for RBD device is larger than local SATA SSDs. That's the reason. Okay, this is the another test we've done here. So we tried to keep those keep a SSD cache on those computing nodes. For example, on the first query, it might read those tables from the Redis gateway here, and then promote those data to a compute caching node, maybe SSD based. And then for the second query, later it can access data locally instead of querying Redis gateway in the downside. So we did small tests with Aluxu, which is acting as a caching tier, but it's co-located on the compute nodes. We then found we actually picked several I/O-intensive queries from those 54 queries of TBCDS, and we found that with those I/O-intensive queries, some queries like query 68, the performance improvement is like the query time reduction is 37%. So the performance improvement is like 100%. So this approves, actually you can do a compute side caching, and this can improve your I/O-intensive queries performance a lot. Okay, so we then did a performance comparison with remote HDFS, which is more meaningful for the existing Hadoop deployment. So this is remote HDFS configuration. Basically, it's the same as the previous architecture. Instead, we use 7 SATA SSD as the data device in the storage tier. So this is the final comparison. We can see with Parquet format, object store, Bigdata over Ceph object store is almost similar as Bigdata over remote HDFS. So with the awk, the light blue pillow here, we don't know what's happening there, but I guess there's still some bug inside S3A driver. But at least for Parquet, we can see the performance is on par. So this is the detail. This is a detailed analysis for Bigdata over cloud and remote HDFS. We then did a micro benchmark DFSO read-write test, and then we saw, if you look at the deep blue pillow here, so for DFSO write, HDFS is better than Ceph, but with the reason is HDFS is actually block write, but for S3A you have to do a rename. For example, if you're writing object A, you have to write temp A first, and then rename that object to A. This is a very compressive operation inside object store. And then we then also did the TerraSort. This again approves this our conclusion. So we found in TerraSort the reduce time is much bigger than HDFS-based solution. That's because there's lots of rename operations during the reduce stage. But there's actually lots of ongoing rename optimizations. IBM has, I've listed several ones here. IBM has a Storecat, which connect to Swift-based storage, and then use a direct output, which eliminates the rename stage. And also, there's upstream work called S3A committer. I think this is recently get merged during Hadoop 3.0. Basically, it just eliminates the rename stage, and then you got much better performance for write workloads. Okay, so renaming can actually be improved. Okay, so to do a summary, from our tests, actually, Bigdata over Ceph data lake is functional ready, and also the performance is on par with remote HDFS. And also, we found that with all-flash-based Ceph, the TCO is actually better than HDD-based. A 10-node SSD-based cluster is on par with 16-node-based HDD-based cluster. And for the next step, we're going to expand more workload, for example, streaming workload. And also, we are going to test the rename optimizations included in the latest Hadoop distribution. And also, we're trying to see if we can speed up the shuffle device with local NVMe device or remote RBD device. Last one is we're going to test if the compute side caching can improve performance for different workloads other than batch analysis. So I think this is it. I have some details back in the backup, but I want to, I think we can skip that. So.
Great. If anyone has any questions, if you could step up to the microphone because it's being recorded and just so that everyone could hear it, that would be fantastic. Thanks.
I come from an Hadoop 2 background, so I don't know much about Hadoop 3. Mm-hmm. So coming from an Hadoop 2 background, Bigdata works in a logic where you ship the code to the data. Mm-hmm. So in this case, are you shipping the code to the Ceph clusters? Because in that case, there's some kind of a network push of data across the network because the data should be made local to the code. How are you handling that?
Well, the simple answer is it's not. It's not local. So, and one of the challenges when you have multiple analytics clusters and you want to have a shared store, you can't necessarily always push the compute to the data because in order to break that coupling, you lose locality. So whether or not you're using HDFS or Ceph, you're sacrificing that locality for the flexibility you get from having kind of workload-specific clusters. And there is a performance impact, especially if you're dealing with really low latency queries, like if you're doing kind of iterative querying with something like Impala or Presto. But for the types of workloads that we're seeing a lot of people using this sort of use case for, they're more high throughput oriented, and the throughput, the ability of the network to handle the amount of throughput that is necessary for these types of applications is really matured in the last 5-10 years. We have many people deploying 40 or dual 25 gigabit, sometimes 50 or 100 gig networks, and so the throughput constraint is not the same as it was when the MapReduce paper came out from Google. The oversubscription ratio in their data centers was 18-1. The type of fabrics that we see customers deploying these sorts of things, these sorts of workloads onto these days are 1-1 or 2-1 or 4-1. So a lot of the challenges that led to the locality, kind of the locality trick, are less useful today unless you're dealing with really low latency and accessing data that can fit in memory.
Okay, one more question is, when there is an HDFS, we have a name node keeping track of the files of where the data sits. Mm-hmm. But since it's Ceph, what does the name node do? Do you have a name node anymore?
No, there is no name node, and that's something that's somewhat beneficial because you don't have that single point, you don't have that scalability bottleneck, or the small file problem kind of goes away because Ceph is algorithmic, and so the data is being stored via an algorithm.
So do I assume there that there's no health check back from the data node to the name node because both name node and data node daemons are dropped?
Yeah. And this usually people will run like a thin HDFS within each of the analytics environments because Yarn will still log some stuff into there, but all of the I/O to the columnar data or the data set itself is bypassing that completely and is going to like the S3 interface at the Ceph gateway and is coming directly into the containers that are managing the workload.
All right, thank you.
Mm-hmm.
Hello. I noticed how you multiplied the Rados gateways and you collocated them with OSD nodes. Mm-hmm. I wonder if you considered collocating them with compute nodes instead. I believe that would drop the network traffic in half.
That's a good point. We've actually had a lot of recent conversations about exactly what you described. There is kind of you cannot kind of scale a RGW cluster to really, really large numbers. So if you have lots of clients, there's some internal coordination that they do, and so that might be challenging if you have like thousands of compute hosts or something. And so that might be a barrier there, but conceptually, yes, because then instead of if you have the RGW running on the OSD host, and the client has to hop over the network to get there, if the data is not local to the RGW instance that it's talking to, it still has to pull it from the Ceph cluster and then push it back over. So by pushing it up to the client, you do save. We're having ongoing conversations about making kind of like a thinner RGW that uses less coordination so that you can maybe run one per Nova compute host or one per Kubernetes host or whatever,
Yeah, so similar kind of question, actually. I was interested to see how you got better performance by running multiple Rados gateways on an individual node, still dedicated node at that point. And I was wondering if that gave you a different kind of performance advantage over, just tuning the number of threads in Rados Gateway and CivicWeb.
So CivicWeb is okay, and you can tune it to a degree, but it's not like a C10K web server, right? And there's a lot of work going on upstream to replace CivicWeb with a new backend web server in Ceph called, it's based on the Beast ASIO framework, and you should be able to tune an individual RGW instance to accommodate a lot more traffic. But right now, you can kind of tune CivicWeb up to its ceiling of performance, and then you kind of need to have multiple of them. Yeah. Great. Thank you.
Thank you.